We've already tested 2x2 matrices 4 different ways for positive definiteness. Today we scale up. Behind every positive definite matrix lives a shape, and in 3 dimensions that shape is an ellipsoid. We'll watch a tridiagonal 3x3 matrix pass all 4 tests, then use the Principal Axis Theorem to draw its ellipsoid, axis by axis. Meet our matrix A, a tridiagonal 3x3 with 2's on the diagonal and the negative ones just off the diagonal. The corners contain zeros. Now for test 1, the leading determinants. The top left 1 by 1 block is just the number 2, so its determinant is 2. The top left 2 by 2 block gives 2 times 2 minus -1 times -1, which is 4 minus 1 equals 3. And the full 3 by 3 determinant works out to 4, so our leading minors are 2, 3, and 4, all strictly positive. The first test passes. Notice the pattern. Each determinant grows, and the ratios 2/1, 3/2, and 4/3 will reappear in just a moment. Test 2. The pivots. Running elimination on matrix A produces 3 pivots, 2, 3/2, and 4/3. All positive, so the second test passes. Now look closer. The first pivot is 2/1. The second pivot is 3/2. The third pivot is 4/3. Each pivot is the ratio of consecutive leading determinants. And if we multiply them back together, 2 times 3/2 equals 3, and 3 times 4/3 equals 4. The pivots and the determinants encode the same information from 2 different angles. This isn't coincidence. It's the structure of elimination. Test 3. Eigenvalues. The characteristic polynomial of A factors to give 3 eigenvalues. 2 minus the square root of 2, 2, and 2 plus the square root of 2. Numerically, those are about 0.59, exactly 2, and about 3.41. All 3 are positive. Now 2 quick sanity checks. First, the trace, the sum of the diagonal entries, is 2 plus 2 plus 2, which equals 6. The sum of the eigenvalues is 2 minus root 2, plus 2 plus 2 plus root 2. The root 2's cancel, leaving 6. They match. Second, the determinant is 4. The product of the eigenvalues is 2 minus root 2, times 2 times 2 plus root 2. Using the difference of squares, that's 2 times the quantity 4 minus 2, which equals 4. Everything checks out, so test 3 passes. Test 4, the quadratic form. We compute x transpose Ax, and the result is 2x1 squared plus 2x2 squared plus 2x3 squared minus 2x1x2 minus 2x2x3. Notice the pattern. The diagonal entries of A, all equal to 2, become the coefficients of the squared terms. The off-diagonal entries, each equal to -1, become cross terms, and they get doubled because by symmetry, each off-diagonal entry appears twice in the matrix. There is no x1, x3 term, and that is because the corner entry of A is 0. Now we complete the square. The entire expression rewrites as 2 times the first squared term, plus 3/2 times the second squared term, plus 4/3 times the third squared term. Look closely at those coefficients. 2, 3/2, and 4/3. These are exactly the pivots of A. Since x transpose Ax is now a sum of positive multiples of squares, it must be positive for every non-zero x. The fourth test passes. We've now confirmed positive definiteness 4 different ways. So here's the geometric question. What does this actually mean? The function x transpose Ax takes a 3-dimensional input and returns a single number. Its graph lives in 4 dimensions, but we can still picture what's happening. Because A is positive definite, the graph opens upward, it's a bowl, and its minimum sits right at the origin with value 0. Now slice that bowl horizontally at height 1. The set of points where x transpose Ax equals 1 is the intersection of the bowl with that plane. A closed, smooth surface sitting in 3-dimensional space. That surface is an ellipsoid, the 3-dimensional cousin of an ellipse. Positive definiteness is what guarantees this slice is a finite bounded shape rather than something that escapes off to infinity. Ellipsoids come in three flavors, determined entirely by their eigenvalues. First, when all three eigenvalues are equal, as in the identity matrix, the ellipsoid is a perfect sphere. Every direction stretches by the same amount. Second, when two eigenvalues match and one differs, you get a rugby ball shape. There is one distinguished axis, either longer or shorter than the other two, and the other two axes together form a circular cross-section. Third, when all three eigenvalues are distinct, the ellipsoid is lopsided. It has three axes of three different lengths, like a stretched and squashed football. Now our matrix has eigenvalues 2 minus the square root of 2, 2, and 2 plus the square root of 2. All three are different. So our ellipsoid falls into the lopsided category with three unique axes pointing along three orthogonal directions, each with its own length. Here's a natural source of confusion. The diagonal entries of our matrix A are all 2's, yet our ellipsoid has three different axis lengths, so the diagonal entries cannot be giving us the geometry directly. The truth is this. The directions of the ellipsoid's axis come from the eigenvectors of A, not from the matrix entries, and the axis lengths come from the eigenvalues, not from the diagonal. To extract the shape, we have to diagonalize the matrix. That step is the bridge from algebra to geometry, and it has a name. For symmetric matrices, this bridge is guaranteed to exist and to behave perfectly. There is always an orthogonal matrix Q and a diagonal matrix lambda such that A equals Q lambda Q transpose. This is the Principal Axis Theorem. The Principal Axis Theorem states that every symmetric matrix factors as A equals Q lambda, Q transpose. Here lambda is diagonal, holding the eigenvalues. Q is orthogonal, meaning its columns are unit eigenvectors that are mutually perpendicular, so Q transpose equals Q inverse. That's the gift symmetry gives us. Geometrically, this factorization reads like a recipe. The columns of Q, the eigenvectors Q1, Q2, and Q3, point along the principal axis of the ellipsoid. Lambda's diagonal entries set the lengths. Specifically, the half-axis along eigenvector Qi has length 1 over the square root of lambda I. A larger eigenvalue means a shorter axis. The bow is steeper in that direction, so the level set squeezes in. A smaller eigenvalue means a longer axis. The smallest eigenvalue produces the longest direction of the ellipsoid. Now let's apply the formula to our matrix. The smallest eigenvalue is 2 minus the square root of 2, which is roughly 0.59. 1 over the square root of that comes out to about 1.31. This is the longest half-axis. The middle eigenvalue is 2, and 1 over the square root of 2 is roughly 0.71, giving the middle axis. The largest eigenvalue is 2 plus the square root of 2, about 3.41, and the 1 over the square root of that gives roughly 0.54, the shortest half-axis. 3 numbers, 3 directions, 1 ellipsoid, completely described. The 4 tests detect positive definiteness. The Principal Axis Theorem visualizes it. The equation A equals Q lambda Q transpose isn't just a factorization. It's the full geometry of the matrix, written in coordinates the shape itself prefers.